All right. Well, let's start talking about the connection between the uncertainty principle and the wave properties of matter. Hang on. Very good. Here's the uncertainty principle. Delta P, delta X greater than or equal to h bar over 2, and delta E, delta T greater than equal to h bar over 2. All right? Last time, we drew a cartoon picture to help us understand this. Get a kind of mental picture. The picture is supposed to represent matter waves. For a particle for which the uncertainty in momentum is very, very small, we can think of that as a matter wave where the wavelength is very, very well known. That would be a sinusoidal wave. Sinusoidal waves have no beginning or no end. So there's no information in that waveform that tells us where the particle might be found. At the other extreme, we have a wave pulse, like this. For this wave pulse, even without knowing any details, we have a pretty good idea of where the particle represented by this wave pulse might be found. But we don't really have any idea of the wavelength of the pulse and thus the momentum of the particle. Okay? That was our mental picture. Now, what I want to stress here is that this picture is only telling us something about waves, all right? It's not telling us anything about quantum mechanics. It's simply saying that there are different types of waves. Extended waves, like sinusoidal waves, and wave packets of shorter and shorter length down to a wave pulse, like the one drawn on the bottom. And that makes you think, is there some analog to the uncertainty principle that just has to do with the property of waves? Well, it turns out there is. And this is called the time bandwidth product. Okay? We could focus on either of the expressions of uncertainty, but we'll focus on time energy uncertainty now. Here's the idea. The time energy uncertainty principle says delta E, delta T is greater than or equal to h bar over 2. But we know something else too. We know that the de Broglie equation relates energy and frequency. The energy of a particle is hf, okay? Or multiplying and dividing by 2 pi, we have h over 2 pi, or h bar, times f times 2 pi, which is omega, okay? Thus, the uncertainty in energy can be written as h bar times the uncertainty in frequency omega, okay? That being the case, we can substitute that back into the previous expression, and we find h bar delta omega times delta t greater than or equal to h bar over 2. And when we do that, we see something really interesting. The h bars cancel, all right? This isn't actually a quantum mechanics expression at all. It's just an expression about waves. And it says that the uncertainty in angular frequency times the uncertainty in time is greater than or equal to 1/2. This is the time bandwidth product. Okay? And it's telling us that a wave pulse of shorter and shorter lengths or durations has a higher and higher uncertainty about its frequency. Okay? And what's interesting is that this is just an expression about classical waves. All right? And so this is telling us the uncertainty principle can be thought of really as just the time bandwidth product plus the de Broglie relationships. Okay? So that makes it a little less mysterious. All right. Here, let's stop this short video here, and then I want to talk further about wave packets in the next one.